Okay, let's start the lecture today. So in the last lecture, we barely started on the multi-agent reinforcement learning, and we first talk about a basic model called the normal form game. So we first reveal what is normal form game. As we mentioned earlier in the last lecture, we say we will always start from the very basic setting, which is the games without any states or any transition. So this is what normal form game. So very easily, normal form game can be specified by a utility matrix, which is a reward or utility of A and B, and A is the action of the max player. While B is the action of the main. Okay, and this R kind of like denotes the utility, the reward of. So essentially why we call the two pair, one is max player, the other one is min player, because max player always want to maximize the reward, and the min player always want to minimize the loss. Well, this is like zero sum game. So essentially the gain of one player is actually the loss of the other player. So this is how we start. Basic formulation for the normal form game. Okay. It's very simple. It's just you have one utility matrix where the rows are actions of the max player and the columns are the actions of min player. Okay. So this is basically where we stop in the last lecture. We just talked about the basic formulation of the normal form game. So today we'll talk more about the solution concepts and how we're gonna solve those games and move beyond this stateless, transitionless games to the Markov games where we care about for multi-reinforcement, right? So first, for this normal form game, the first thing we wonder is what is the optimal strategy for this normal form game? Like what is the final objective, like the goal we want to climb? So in games, it's very different from single agent reinforcement learning or like bandit scenario. Where bandit scenario, we just want to find the best arm, and a single agent scenario, we just find the optimal policy. Well, here we say the most important feature of the game is that your opponent is no longer fixed. It's not like the environment that is fixed. Your opponent is actually adaptive. So we're not just finding some single policy that achieves the maximum value or anything. We're actually aiming to achieve some equilibrium between the players. So one very famous notion of the optimal strategy or like what is the concepts we're trying to find for the multiplayer game is called Nash equilibrium, proposed by John Nash. So conceptually, the Nash equilibrium is talking about some strategy, mu and mu, which satisfy the following high-level intuition, which basically says no one has anything to gain. By changing only one's own strategy. basically means, for example, if mu nu is a Nash equilibrium, that means if we reach this strategy equilibrium, mu and nu, and if my opponent is always playing nu, okay, he's already fixed, and I decided to change my strategy. I no longer play mu strategy, I play some other strategy. I won't gain anything. And similarly, for my opponent, if I always stick with playing with mu policy, and if my opponent is decided at some point he no longer wants to play mu and he wants to play some other strategy, he won't gain anything. So in this case, it means we reach a Nash equilibrium. Condition on other player fixed, they won't change. There is no incentive for me to change my strategy. Okay. So this is like the like English definition. So we'll discuss like whether those things always exist and how to reach such kind of equilibrium. So in order to talk about Nash equilibrium, there are a lot of things we need to talk about. I think the first most important thing is we need to talk about this strategy. What do we mean by strategy? So classically, one very easy thing you would think of about strategy is the pure strategy, so-called pure strategy. Pure strategy is the very basic strategy that each player essentially this is the most easy strategy. Like you just commit to an action and you always play that action. This is your strategy. So let's say, suppose we have some A star, B star, that is a pure strategy Nash equilibrium. Then by definition, we have the following. That's R, A star, B star, which by the definition of Nash equilibrium, if opponent is fixing A star, then like choosing B star won't actually decrease the reward. Actually, won't actually increase it won't actually decrease R because the second pair is a mean pair. So basically, you can say this is even less than the minimum. Essentially, this is achieving the minimum. And on the other hand, by definition, if my opponent is fixed, so he's fixing playing B star, no matter what I change, I won't increase the reward. So this is actually even greater than RA B star. And of course, you can also see this is less or equal to max A, min B, RAB. Because I just adding a max over A in the front, and this is always holds. And similarly, we can also say this is greater or equal to min B max A R B. So basically, this part always holds. It doesn't matter whether it's pure strategy or like other strategy. This is always true. But what we can conclude from the pure strategy Nash equilibrium is we can look at the example of game in the last lecture. which is a rock, paper, scissors game. We say the rock, paper, scissors can be specified by the following game matrix. That is a rock, paper, scissors. And the rock, paper, scissors. This is 0, 0, 0, minus 1, minus 1, 1, minus 1, 1. So if we look at this game, in rock, paper, scissors, we can solve for the max mean of RAB. Max mean means we first pick a row, and then we pick a column that will minimize this reward. So in that case, we realize no matter which row I pick, if the second player, like in the main player, trying to play the worst case scenario, that he can always pick the -1 reward. So in this case, the max mean is actually equal to -1. And on the other hand, we can also find the min max. Min max means that we first play the column, and then we play the row according to which column, and so that we can maximize this reward. So in this case, we can see no matter which column I pick, the row player can always pick certain action so that to maximize the utility to be 1. Okay. So first column you can pick paper to be 1. Second column you can pick scissors to be 1. So in this case, this is actually equal to 1. So we actually now see we reach a contradiction that we say -1 is greater or equal to a bunch of things, and eventually greater or equal to 1. This has some contradiction. So basically it means something is wrong when we like the precondition is wrong. The precondition is like we assume there exists some pure strategy Nash equilibrium, but clearly for rock, paper, scissors there is no such a pure strategy Nash equilibrium. So what we conclude here is that pure strategy Nash equilibrium may not always exist. Okay. So this is why in the game theory, a lot of times we're not only focused on the pure strategy, we actually also focus on a more general class of strategy, so-called mixed strategy. So the mixed strategy, essentially, we're no longer committed to a single deterministic action. The player actually commit to play a randomized strategy that is a distribution over action. So each player plays a distribution over actions. So in this case, we can specify both players' strategy by some distribution. For example, I can specify the mu in a probability simplex A, and nu in probability simplex of B. So those are like probability distribution over action set A and probability distribution over action set B. So the utility of mu and nu, that is if the max player plays strategy mu and the mean player plays the strategy mu, becomes, we can write as f mu and nu and it's equal to summation of A and B, which is mu is the probability of taking action A, and the utility of RAB times the probability of taking action B for my opponent, for the main player. And we can also write this in the matrix form, where we say this is a mu vector times R matrix. R matrix is the utility main matrix of the game, and times the nu vector, where mu vector is A-dimensional simplex, and mu is in the B-dimensional simplex. This is a bilinear function. Where in terms of a bilinear function, in the sense that like when fixed nu is a linear function in mu, and when fixed mu is a linear function in mu. So it turns out when we expand the strategy space to this mixed strategy, we can actually prove in that case the Nash equilibrium always exists. This is due to the famous von Neumann minimax theorem. It says the following, that U and V be the convex compact set. F, U, and V in R to R, which maps the Cartesian product of U and V to a real number, is a convex function. Convex concave function. So by convex concave function, we actually means that when we fix mu, we fix one of the argument of the function, and we only look at the function of the other argument, it's actually a concave function. And if we fix the other input, it's actually a convex function in the first argument. So convex concave just means fixing one is concave in the other, and fix the other is concave in the first. So that basically there are only two preconditions. That is, first the set is convex compact, and second the function is convex concave. Then we have the minimax theorem holds. Minimax theorem holds in the sense that max min of UV is equal to min max So we can see from the pure strategy part here, the very important thing that there's contradiction, and so that we say the pure strategy naturally may not hold is exactly because this max min actually not equal to min max. Max min is actually less equal to min max in this kind of scenario. So this min max theorem basically says when we expand it to the mixed strategy, or like basically here, this F in the mixed strategy case, f is a bilinear function, so this satisfies the convex concave condition, and then we do have this min max equal to max min. And furthermore, there exists a strategy mu star essentially achieve the min max value. In a sense that f mu star is equal to min max f mu mu and equal to max min. So basically, the von Neumann theorem says first min max equal to max min, and also there exists some strategy mu star that basically achieve both min max and max min value. And we see by the definition, this basically says this means mu star is a Nash equilibrium. So the von Neumann min-max theorem basically guarantees that we can imply that mixed strategy Nash equilibrium always exists. For the normal form game. So a lot of times when we look at the game theory, the whole literature is basically trying to find this so-called mixed strategy Nash equilibrium. This is like one of our goals. This is what we call objective. And in a rock, paper, scissors, like in this game, you may wonder what is the mixed strategy equilibrium? Mixed strategy Nash equilibrium. So in that case, we say the mixed strategy Nash equilibrium. Actually, later when we talk about the Nash equilibrium, we always talk about mixed strategy Nash equilibrium. So for a lot of contexts, we will just ignore this like mixed strategy part. You can check, it's just to play all three actions uniformly. That is, I will play rock and paper and scissors with 1/3 condition, with 1/3 probability. And you can check if I play all the action with uniformly and you play action with like uniformly, then this is like Nash equilibrium. Basically, if you keep playing this uniform strategy, and no matter how I change my own strategy, I won't increase any utility for me. Like I will always achieve a 0 utility, which is like by the definition, this is like the Nash equilibrium. So we start talking about this like optimal strategy, starting from like one of the motivations from the game theory, where it seems like we want to achieve some equilibrium. There are also some other notions in the game theory which will be relevant and very important to our case. That is called the best response. So best response, you can easily understand this, what this solution concept is. It's basically just the best strategy to counter the opponent. this is basically assuming if my opponent is playing some fixed strategy, or is for a long time like playing some same strategy, and I want to counter my opponent, and what is the best strategy I should play? So in our two-player zero-sum games, basically we have the best response for both players. First, the best response of the max player, best response for max player. Max player will play the mu part. So if you talk about the best response for max player, we need to talk about it is best response of some min player strategy. So best response in that case, it should be a function of the min player strategy, that is the mu. In that case, essentially it's just R max. I will pick the strategy for the max player so that I will maximize the utility. And similarly, you can also say that for the min player, you can also define it is the best response of some max player strategy mu is defined as R mean of this mu. Okay. So how is this best response related to the Nash equilibrium? It seems like from the first glance it's like very unrelated because this is assuming your opponent is like playing some fixed strategy but not necessarily Nash equilibrium. While the other one seems like talking about both players eventually achieve some Nash equilibrium, eventually achieve some equilibrium. But we actually know since for Nash equilibrium strategy, mu star, we have the minimax theorem holds. We know the following is true. That is, we know f mu star is equal to both min max and also the max mean. Of the utility. On the other hand, we can also look at the second part, this part here. This is basically saying, assuming the max player is playing mu strategy, what is essentially the best response of the min player he can do to minimize the utility function. So this is also equal to max mu, the utility of mu, and if my opponent is always playing the best response of mu. So similarly, you can also say here, for the second part, you can think of it as I first choose the min player strategy to be new, and then the max player just do whatever to maximize the utility according to this new strategy. So this is also equal to min of mu, f of the best response of mu, and mu. So by this equation, we know the second interpretation of the Nash. So first interpretation of Nash equilibrium, that is if both players committed to mu star, and one player won't gain anything by only changing his own strategy. And the second interpretation is here, that Nash equilibrium is actually the optimal strategy. if always facing the best response. So this is second motivation why in a two-player zero-sum game we might want to find the Nash equilibrium. Because in this case, this essentially says if my opponent just knows me very well, and somehow no matter what strategy I play, my opponent just always magically play my best response. Okay, he just played the strategy that counter me the most. In that case, if I still want to maximize the utility, what is the optimal strategy I can do? And this is saying you should just do mu star. Okay, any questions so far? So once we clear with this like normal form game, we can move to the Markov game. So because this class is about reinforcement learning, so we will always dealing with things that with like a temporal correlation in it. So we will introduce the states and the transition. Second part is Markov games. Markov game is essentially the normal form game. With state and transition. We can also think it is an extension of MDP to two-player setting. On two-player, but in general, you can also extend the Markov game to a multiplayer scenario. So similar to MDP, we can also just specify the Markov game by the following number of components. The first is S. Essentially A and B, and also P, R, H. We're familiar with many of the stuff. The first is this curly S is again a set of states. And A is the set of action for the max player. And B is the set of action for the wing pair. And finally, we also have the transition and the reward and the horizon. So slightly differently is the P, that is the transition, which we originally is the probability of the next states, condition on current states and action. And the only difference here is because it's a multi-agent problem, so it's not only condition on action of the one agent, but also condition on action of the other agent. So basically this depends on both action A and B. And we also have R reward, immediate reward that also depends on both A and B, both action of the two players. And finally, H is the length of each episode. So similar to the reinforcement learning, after introducing the formulation, and we will talk about the value of policy and those basic concepts. So here, the policy, we have a policy for both players. So we again denote it as mu and mu. Mu for the max player and mu for the min player. So the mu is again can be decomposed as a policy at every step. And from H equal to 1 and to capital H. It's the strategy of the max player. Where here it's very important, we should always consider the randomized policy that mu H is defined as S, map S to a distribution over A. The reason we should always consider the randomized policy is basically we already see in normal form game that you can think is an easier case, special case of Markov game without any state and without any transition. There, if we're interested in finding the Nash equilibrium, we already proved like pure certain Nash equilibrium may not exist. That means essentially, if we restrict our attention to deterministic policy, then we may no longer be able to find any Nash equilibrium. So that's why here we always want to find, look at the randomized policy. And similarly, we can also say this mu is equal to mu H, H from 1 to capital H, and it's the policy of the mean player. And again, the mean player strategy at every step should also be a randomized policy. The other thing we kind of read from this the notion of this policy is we kind of say for policy, both player will take action only based on states. But not the action of the opponent. So this essentially is modeling some simultaneous game. Essentially means at every step H, both players are taking action simultaneously. They basically, with this game, will after player taking some previous actions and transition to some new states, and at new states you can see the indicator. Basically, you can see the state index, And then both players will take some action according to the states, and they cannot, like, for example, wait till my opponent doing some action and then I take some action or something. It's like simultaneous. It's a game with simultaneous moves. Finally, we'll define the values. That's BH, mu. The values is always Q value or V value. And Q value, no matter Q value or V value, the value will always depend on the policy of both players. So we can define the BH mu h as S. And the value definition is basically the same. That is expectation if both players play according to mu and neo strategy, and a summation of the future utility. H prime, starting from H to capital H, RH prime, SH prime, AH prime, BH prime. Conditional SH defines. Similarly, we can also define the Q value. Mu, that's the summation of the cumulative reward. Future. Condition on current state is S, and I'm taking action A, and the opponent is taking action B. Assume you're very familiar with this, there's basically no difference on the definition of value curve for the between the multi-agent version and the single agent version. So once we define the value, we can easily, the next step in the single agent is like we write out the Bellman equation. And this actually for fixed policy part, fixed policy mu there is also basically no difference. Let's write out the QH mu SAB. RH SAB plus pH and the VH plus 1, the value at the next step, mu SAB. And the VH mu S is equal to summation A and B. The only difference is now that the value, the policy has like both players has different policy. So we say this is a summation of mu h A given S. This is the probability over the action of the max player, and then QH mu SAB, and we also take the integral over or summation over the probability of the second player, B over S. So far for the fixed policy, there really not much difference. Very similar to single agent version. So the part we need to pay more attention is the optimal policy part. It's a little bit different because we say we no longer just want to optimize it to one direction, we just no longer just want to maximize it, we want to find equilibrium, we have the best response concepts. So we will slowly develop all those concepts and how we're gonna have the equivalent of Bellman optimality equation to those concepts. So the first concept we will begin with is the best response. Because this is just slightly easier, that is, we assume my opponent is fixed, and I just want to find the strategy to counter that. So we can actually prove for any, this is claim, for any fixed strategy of the max player, mu. There exists a best response we denoted as a new dagger of mu, so that we achieve the following for any state S. And step H. We have the following that is true, that is the value of mu, and this best response strategy mu dagger is equal, on any state S, is equal to the minimum of mu and the VH mu and mu S. So if it only has like one single state and one single step, there isn't anything to claim. Okay, you're just saying there exists some strategy that minimizes that, of course, it exists. But what it claims here is because this is for MDP, and we can actually have one single best response, which is one single policy, which would denote in this notion, that can achieve the minimum value, like essentially the simultaneously counter the opponent's strategy mu on any states S and any step H. So this is the important part that it can achieve simultaneously. And the reason is actually not that hard to see. The reason is because when mu is fixed, that is, if the max player strategy is fixed, then to the min player, this Markov game becomes an MVP. So you can integrate out the max clear part. And then, because it always play a fixed strategy, so we can, whenever doing the transition, we can integrate out the probability of the max clear and the reward also the same. So from a mean clear perspective, as if it's just an MDP, because my opponent is no longer adaptive, it's just fixed. So whatever the result hold for MDP holds here. And in this case, we know for MDP, we can find an optimal policy so that it achieves the optimal value simultaneously on all state and step. And this is essentially the same thing. That when my opponent is fixed, I can find the best response that achieves the minimum value at all state and step simultaneously. In this case, we will also do some notation. We always denote that's VH mu dagger as a shortage for the VH mu dagger mu. It's a little bit complicated in this notation, but basically this value is saying if one player is fixed, we play mu, and the other players play the best response, and what is the value we can achieve. And so similarly, you can also define some strategy mu and mu star that is optimal against the best response. And this, we say VH mu star S, mu star dagger S. This thing is equal to the maximization of mu, VH, mu dagger S. So essentially mu star is the best policy if always facing the best response. That is, in this case, whatever the policy that always facing the best response, mu star achieves the maximum value. And we also know this is equal to minimax, or max mean. VH mu S. And similarly, we can also define the best response for the opponents, for the mean player. So we say this. And we also have this equal to the mean mu VH dagger mu S and equal to mean max VH mu S. So in the normal form game, we kind of notice the second interpretation of Nash equilibrium is actually Nash equilibrium is exactly the optimal strategy if always against the best response. So here we can in fact also prove this is the Nash equilibrium. This mu star is also the Nash equilibrium for the Markov game. So basically here, furthermore, we can show minimax theorem holds. although this is like beyond the reason of the original von Neumann minimax theorem, but you can check for this like Markov game scenario by dynamical programming. This is actually true. So although the value function is no longer convex concave, in the original minimax von Neumann minimax theorem, they require to be convex concave so that the minimax theorem holds. So we can check by dynamical programming. This is true. So the claim is basically says there exists some strategy mu star, which is actually also the optimal against best response, so that we have the VH mu star S is equal to the minimax strategy, the minimax value, VH mu S, and also equal to the max mean strategy, the max mean value. For any S sandwich. So in this case, mu star are the natural. And they are also the target of our learning algorithm. Yes.
So are the optimal policies fixed? Because it seems like the best response depends on having a fixed strategy,
Right.
but then the optimal policy depends on the best response.
Right. So this is like you're right. If the policy mu is changing, then their best response is also changing. So what we say here is no matter what strategy this max player is doing, if assuming opponent is always playing the best response to him, so in that case there is a policy that can maximize that value. It's kind of like the best policy against best response.
Oh.
And this is defining this way. So it's like minimax strategy in some sense. Also the other is max min strategy. And Nash equivalent is basically just this min. It's both min-max strategy and also the max min strategy. And this is why we're using finding Nash equivalent. Okay. Any other questions? So now we're clear with what is our objective-like solution concepts. We start from the best response, and then we also have this Nash equivalent. So basically, almost everything is the same. All we justify is like we can very easily extend the normal form notion, like both in terms of both best response and the Nash equivalent to the Markov game scenario. But now the next question is, how are we going to measure the suboptimality? Like this, we know our objective is finding this Nash, But for example, if I find the policy pair, so this is our topic, it's automatic. So for example, if I find a pair of policy, mu and mu, and we know the Nash equilibrium is what we want to find, but in reality, we never be able to find infinite close to this mu and mu. We always have some suboptimal automatic, like in the simulation case we're talking about the epsilon suboptimal policy. So in this case, how are we going to measure the closeness between this mu and the Nash equilibrium? So we will use the metric of a Nash equilibrium is actually the min-max policy or the max-min policy. In a sense, like it's the best policy against the best response. We'll use this metric to measure the suboptimality. Use this metric to measure suboptimality. So naturally, we should first look at the suboptimality in nu, in the main player's part. And what we can do is we can look at if my opponent is exploiting me, if the max player is exploiting me. So this is the utility max player can receive, and also the loss of the mean player if I play mu. And how far it is to the truly optimal policy if always facing an opponent. That is the Nash policy. And minimize the mean prime, and d1 dagger, mean prime. We know this is the best mean pair strategy if always facing the best response. And this is one of my current strategy when facing the best response. So I look at this difference as one part of the suboptimality. And by symmetry, we can also look at the max player suboptimality in this way. So which is what can be achieved by the optimal policy against best response. Subtract what can be achieved by playing my policy mu against best response in S1. So it seems like this is suboptimality of the second player, the mean player, and this is suboptimality of the max player. So one very easy thing is we can actually just summation them together. And we also notice one very important thing, that because for this Markov game, Nash equilibrium exists, this mean strategy is actually achieved at Nash. And this max strategy is also achieved at Nash. And we further have min max equal to max min. So those two parts are actually equal. So we're subtracting subtract and plus an equal term. So eventually this leads to a measure of suboptimality by duality gap. So this metric eventually just equal to V1 dagger nu S1 and subtract V1 mu dagger S1. That is, if the mean player play policy nu, what is the best response gonna exploit to get in the utility? Versus if the max player play mu and what is the best response of the mean player can get the utility. And we look at this so-called duality gap, and this is suboptimality. And we notice for the Nash equilibrium, if mu and nu are truly Nash equilibrium, this duality gap would be equal to 0. Mu and mu. So we notice that duality gap is always greater than or equal to 0, and therefore Nash equilibrium duality gap is equal to 0. So this is why we are considering this objective. So we say mu nu is epsilon optimal. If we have the following, that is the duality gap of mu nu is less than epsilon. Okay. So those are like abstract concepts about the solutions and what is the subalternating, how we measure the epsilon subalternating. And then next we will talk about the algorithms, how to find the best response and the Nash equilibrium. So similar to reinforcement learning, the single agent setting, we will consider the easiest case first, that is the planning. First consider planning. And just recall, planning is the setting that if we know the transition and also the reward. So in the single agent reinforcement scenario, basically what we're doing is just using value iteration, and value iteration is a dynamic programming version of the Bellman equation. Bellman optimal equation. So the key part here is that we will establish something similar to Bellman optimal equation for the multi-agent scenario. So we'll divide it into two parts. First one is if we just want to find the best response of some fixed policy. So what we have here is we can essentially write out the Bellman optimal equation for this one. And we notice, as we mentioned earlier, if one player is fixed to play some mu, and in the perspective of other player is just an MVP. So we can essentially easily write out this Bellman optimal equation. It's just equal to arch S A B and plus pH plus 1 mu dagger SAB. And similarly, we also have the value S is equal to mean of the mu h summation AB mu h a given S and QH mu dagger SAB and mu h the only difference is now we no longer have the policy new, and instead we kind of replace new by minimizing over it. So it's similar to the MDP case where we're doing the maximization over the Q value here because we write the version for the min pair. And you can similarly write the similar version for the max pair. It's just replace this min by the max. So this is essentially the same as the MDP Bellman updates, Bellman automatic equation. So the second is we want to find a Nash strategy. This is a slightly more interesting one for Markov game. It turns out for finding Nash equilibrium, we can basically write out optimal strategy, Bellman optimal equation in a similar fashion. So we'll see. Let's use the Q star to denote the value of the Nash equilibrium. And we can write out that Q star HSA. I think the Q value updates will always be the same, that is equal to RH SAP plus the BH plus 1 star SAP. So the only different part is again how V value is updated according to Q value. And now we no longer have any strategy mu and nu. It turns out we're replacing here is simply that just the value of the Nash equilibrium is equal to min max. We can also replace it by the max min because the min max theorem holds, so basically both values are equal, so it doesn't matter which order you're doing. And summation of AB, mu h A LMS, and Q star h SAB, and then we have the new h B given s. So now we see, basically for the Markov game, the only different part when we replace the Bellman optimal equation is we replace the max originally in the single agent scenario by the min max. This is the Bellman optimal equation. Yes.
Wait, so once you have the Q star and V star, then how do you go back to the new policies?
Oh yeah, you basically the same thing like in the single agent setting we're doing the greedy policy. That is, we're doing the max over the Q. So here again we can also just whenever I have Q, I can solve this min max again to find a Nash. Whenever I have this Q, this is like for each state I have this become a normal form game. So I can find a Nash equilibrium for the normal form game. This becomes the strategy for the single state.
It's not always just like a hard max or a acceleration.
It's not our max. Yeah, it's like it's again like a mixed strategy. This is a very good question. Okay. I guess I will stop here for this week, where we finished talking about the formulation of Markov game and the objectives, and also the planning algorithm. So starting from the next lecture, we'll talk about the learning algorithm from both the heuristic perspective, like what is the current a lot of empirical algorithms doing, and also from the principled perspective, like starting from this Bellman optimal equation, how should we design the algorithm for this multi-agent reinforcement model?